Hello, my dear J Warriors. Good evening, good evening, good evening in the Roar series, which is your live series on YouTube, absolutely free of cost for all the JEE aspirants, whether class 11th, class 12th, or droppers. And that too in pure English, because this is a JEE English channel and the number one JEE English channel in the country, and in fact, the first one too. So, let's begin with the class. And today we're going to do the lecture one of capacitors, where I will be talking about what is a capacitance, how to measure it, what are the different types of capacitors that you have, what is the energy stored in the capacitor, what is the meaning of a dielectric. Then in lecture number 2, I'll be combining both resistors and capacitors together to see the different combinations, be it series, parallel, or dielectrics are kept at different places. There is a gap and all the other combinations. So the combination of resistors and capacitors will be a combined lecture as lecture number 2. Lecture 1 mainly understanding the capacitors, the types, the force between the plates, the energy which is stored, what is the dielectric and what are the effects. Okay, so that's what the flow of the lecture is. And welcome aboard. Nice to see all of you. The duration of the session, SHK, we do not know. I do not plan my sessions as to I have to finish it in 1 hour or have to finish it in 3 hours. As long as it takes, but give or take 2 to 3 hours around that time. Yep. Hello Sadia, hello Nikhil. Can we have the PYQ sessions live? Nikhil, the problem with PYQ sessions live is that we do not have the time slots. So that is why we are recording, number one. Number two, the thing is, in the PYQ sessions, it's question, answer. So more than concept, then application, then understanding, then PYQ, then, different levels. So it's a very different ball game because it is just pure question and answer, and I don't want any other talking or anything. So that's the reason why we are keeping it as a recording. I know watching the recording as a live might have a different expectation, but I feel with the given time in hand, it is better you can utilize those lectures as recording, even watching it at 2x or 1.5x speed, right? Makes sense. Hi, Brian. Hello, Soumya. Good evening. Current electricity, second part after this, Mr. IIT. Capacitors, lecture 1, current electricity, lecture 1. After that, lecture 2 of both of them combined, combination of resistors and capacitors. I hope that made sense. Okay, and by the way, everything else is updated. In case you have missed any of the previous classes, let me remind you, it is there right over here in the jungle book. Where is our jungle book? Jungle book is somewhere here. Where is our jungle book? See, jungle book. Link is here. So this jungle book will open up all the classes for physics, chemistry, mathematics. People are asking, sir, lecture 2 Gauss law. Guys, it is there over here. Okay, notes, DPPs, everything has been uploaded for all the 3 subjects. Okay, in case you have missed any of the previous classes, you can check it out. All the notes, DPPs, lecture video, the date, everything has been mentioned over here. So let's begin. Now, first of all, how does a capacitor look like? Some of you might know it if you have taken electronics, but if you haven't, well, it looks something like this. Have you seen this somewhere or the other? Maybe behind the TV on a computer, or maybe some electronic appliance, maybe a radio, maybe AC, maybe fridge. Have you seen this? Yep. From Ekalavya will start towards the end after close enough to January attempt. Okay. Yeah. Yep. Mr. IT, I hope that was clear that current electricity will be done in parts. Yep. So definitely you have seen this. So this is what a capacitor is, and capacitor means something related to capacity. So what kind of capacity does it have? It stores the charge and hence ends up storing the energy. But this energy is not any random energy like gravitational energy. It stores electrical potential energy. And this electrical potential energy can be used to do electrical work. For example, well, I didn't bring my phone today here, but yeah. Anyways, you have seen the flash in your phone. There is a sudden burst of light, and huge amount of light comes for a fraction of a second, and then you get a dark area, lightened up, and you can see a very good image being captured by your mobile camera. When that sudden burst of light comes, a lot of energy is used, and that energy can't be provided by the battery. So what happens is it gets stored in a small device like this one over here, which is called as a capacitor. It stores the energy. The moment you turn on the flash, it gives that sudden burst and all the energy gets dissipated in a fraction of a second. So if you try to click next photograph immediately, it's going to take some time before the capacitor charges up again. It has to gather all its energy, just like a superhero or an action figure. He uses all the power and then it has to regenerate and energize itself. So it energizes and it gets ready for the next flash. And this is also used in this concept rather is used in different applications. You might have also seen in movies where they try to revive the person using two conductors. They put it on the chest of the person. Yes, defibrillator, correct? So you will see that the same concept is used. Those devices again are connected to capacitors. The capacitor stores the energy and the electricity is stored in there, and when you connect it to the chest of the person, that charge flows into the body and you try to revive the person. So that is also the concept of capacitors. Because circuits part will be done in lecture number 2. Yeah, I hope this is very clear. This is very clear. Yep. All right. Awesome. So capacitor is simply put a energy storing device. Have I put it somewhere? Yes, it's nothing but an energy storing device. Okay. It is just made up of two conductors. One can have some charge, another can have some opposite charge. Now the moment the charges are opposite, what happens? The electric fields originate from the positiveness and end up at the negativeness. So this electric field is a testimony, or rather it tells me that there is energy in that region. So you take two conductors, you charge them oppositely, and you see the field lines starting from one point and moving towards the negative charge. This electric field represents that there is energy in that region. And if I somehow use this charge up, I discharge the conductors, these electric field lines will vanish, which again tells me, hey listen, the energy has gone. So that's why you need conductors to store, or rather you need conductors which can get charged up, and those charges create that electric field which then store the electrical energy. So capacitor is just made up of conductors with charges, electric field lines which store the electrical potential energy. Depending on how those conductors are arranged and what is their shape, you get different categories of capacitors. Like you can have two parallel plates storing the charges. Then it will be called as a parallel plate capacitor. You can have two concentric cylinders. Inner cylinder has, let's say, positive charge. Outer cylinder, example, has negative charge. So you will see electric field lines go from the positive cylinder to the negative cylinder, and there is electrical energy which is stored in the field inside the cylinder. So then it will be called as a cylindrical capacitor. You can similarly have a spherical capacitor where there are two concentric spheres, one positive, one negatively charged. So the electric field naturally goes from the positiveness to the negativeness. So that field ends up storing the electrical energy in that particular region. That is called as a spherical capacitor. You can similarly make any n number of types of capacitors. You need not stop at these three. You can make a square capacitor or like a cube capacitor. You can make something else also. It's completely up to you. But in JEE syllabus, we just study these three capacitors: parallel, cylindrical, and spherical type of capacitors. Till this point, I hope this is clear. Yes, Tom, it's like a dipole. Yes. Sparkle BP, you are very smart, but I'm not going to read your statement, right? You think we are fools out here, right? Yeah. So please go try this nonsense with somebody else. Okay. Now, now the symbol of a capacitor, the symbol of a capacitor is simply put like this, because capacitor will have conductors. A capacitor is made of conductors, and because I clearly told you, second, because I clearly told you that one of the conductors will be, example, positively charged. The other conductor, let's say, will be negatively charged, and you will have electric field lines going from the positive to the negative charge, which stores the energy, which stores the electrical potential energy. This charge also depends on how much voltage you applied to the capacitor. This particular charge, let's say it is plus Q over here, it is minus Q over here. This charge depends on the voltage difference between the two conductors. And why not? One is positive, one is negative, 100%. There is a potential difference between the two conductors. Or else, why would electric field even go from one side to the other? Remember, electric field always goes from the higher potential to the lower potential. So there is a potential difference. Now, if you increase this potential difference, this will become more positive and this will become more negative. You increase the voltage difference even more. There will be even stronger electric field. Stronger electric field means the voltage difference becomes even higher and the charge stored on them also proportionately increases. So here I would say Q is basically the charge on the capacitor, the charge on the capacitor, the charge on the capacitor. Remember that. But you should also know one small thing, that the net charge, on a capacitor is always going to be zero, because if this is plus 2 coulombs, this will be minus 2 coulombs. 2 and negative 2 will make it 0. But we never say the charge on a capacitor is 0, because then every time the charge on the capacitor will be 0, then what is the point? So we take the magnitude of the charge, that's why I put mod, the magnitude of the charge on any one of the conductors as the charge of the capacitor. So whenever a question comes or whenever we refer to what is the charge on the capacitor, we are not talking about the negative or the positive, we are talking about the magnitude of the charge on the any of the plates or on any of the conductors. Is that absolutely clear, my dear warriors? Won't they attract? Definitely, Niku. Why not? They will definitely get attracted. In fact, we'll be calculating the force also between them. Yep. Yep. I hope that is very, very clear. Now, like I said, this charge is directly dependent on the voltage which you apply between the conductors. So the charge on a capacitor is directly proportional to the potential difference between the conductors between the conductors. Basically, Q is directly proportional to the voltage difference. You want that proportionality to be converted into equality. You will get a constant of proportionality, which is C, which we call it as the capacitance. This is the capacitance. This is the formula for it. So the charge on a capacitor is the capacitance multiplied by the potential difference. Is the capacitance multiplied by the potential difference. As simple as that. Now this particular capacitance depends on the shape, the size, and the geometrical placing of the conductors and also the medium between them. Very, very important. This capacitance is not dependent on the voltage, nor is it dependent on the charge. If you think that, sir, if I increase the charge, will the capacitance increase? No, it's the other way around. If you increase the capacitance, then it will hold more charge for the same voltage. But if you think I increase the charge, capacitance will increase. No, rather it will have more voltage. This capacitance completely depends on what is the shape, nature, like whether it is cylindrical, whether it is spherical, whether it is plate type, how large is that plate, how tall is this cylinder, what's the radius like, what's the medium between these two cylinders or this sphere, or what is the medium between these two plates. These are the things on which the capacitance depends. These are the things on which the capacitance depends. Yes, Arborine, it's a scalar quantity. It's a completely scalar quantity. Yep. I hope this is absolutely clear. I hope this is absolutely clear. I know some of you are also worried. Sir, if these plates are oppositely charged, sir, if these conductors are oppositely charged, won't they stick to each other? Aren't they like dipoles? Won't they attract? We'll come to that. We'll be talking about the force also between the plates of a capacitor. Don't worry about it. I hope till now it is clear. This capacitance does not depend on the voltage nor on the charge. Rather, it's the other way around. But rather, this capacitance depends on the geometry, the shape, the size, and the nature of it. What's the unit of capacitance? It's very simple. See, if Q is equal to C into V, therefore C will be Q divided by V. So, if you store 1 coulomb of charge on a potential difference of 1 volt, then the capacitance is said to be 1 farad. 1 farad, the symbol for that is F. So 1 farad is 1 coulomb upon 1 volt. Usually, capacitances are not in farads. What you see in the computers on the electronic devices, the capacitors typically, the one which I showed you right over here, these capacitors typically have a capacitance of some nanofarads or even picofarads. If it's a microfarad, it is considered to be a very good capacitor. Imagine microfarad is like a good capacitor. It's like a normal student, an average student going to section D or section E and becoming the topper. Okay, so microfarad is a very good capacitor. Millifarad is very, very good. 1 farad is a very amazing. It's like a god type of capacitor. Like really, you are having 1-2 farad capacitance. It's a amazing achievement. Okay, understand that. So usually capacitances are very teeny meeny. Yes, the capacitances are usually very teeny meeny. Right. Awesome. Yes, Dhanirishwaram, it is Q by V. So what does it depend on and what does it not depend on? Everything has been mentioned clearly again. I'm repeating this. The capacitance only depends on the geometry and the medium. It does not depend on the charge and the voltage. Keep that in mind, because a lot of people think if Q increases, C also increases. No, if Q increases, voltage increases, capacitance depends on something else only. Okay. So here is a question. A capacitor gets a charge of 60 microcoulomb when connected to a battery of 12 volts. Calculate the capacitance of it. Since we know charge is equal to capacitance into voltage, charge is how much? 60 microcoulomb. So 60 micro is over here. Capacitance, that's exactly what I have to find. EMF is basically 12 volts. So therefore, capacitance will be 60 divided by 12 micro. So 60 divided by 12 is 5. So 5 microfarad is the correct unit. So capacitance will be 5 microfarad. As simple as that. Right? Straightforward. Moving on to the next question coming up on your screen. Here it is. The potentials of the two plates of a capacitor are 10 and minus 10 volts. The charge on one of the plates is 40. What's the capacitance of it? Okay, again, a very straightforward question. Again, using Q is equal to C into V. Charge stored is 40 coulomb on any one of the plates. Capacitance, I do not know. What is the voltage? Should I take it as 10 or should I take it as minus 10? As per the given information, using the symbol of capacitor, if one of the plates is plus 10 volts, another place is minus 10 volts, the potential difference between them is not 0 or 10, rather it is 20 volts. 10 and minus 10, obviously what's the difference between them? It is 20 volts, right? 10 minus minus 10 is 10 plus 10, which is 20. So 20 should be over here. Hence the capacitance will be basically 2. Hence the capacitor will be basically 2 farads. I hope this is absolutely clear. Yep, option number A. Now let's calculate how much is the capacitance for different geometries. But before going there, I have a simple question for you. Imagine I tell you that there is a conductor over here and there is another conductor over here. You might have to think of Gauss law electrostatics a little bit. And I tell you, listen, the charge on the capacitor is Q. So you will say, okay, sir, there is plus Q over here and there is minus Q over here. My question to all of you is, where are the charges? Because there is one side here, another side here, another side here, another side here. One is the outer side of the left plate, two is the inner side of that left plate, three is the inner side of the right plate, four is the outer side of the rightmost plate. How do you think the charges are distributed? Option A, B, and C, and D. Okay, how is it going to be distributed? So answers are q 0 0 minus q, or 0 q minus q 0, or is it q by 2 q by 2 minus q by 2 minus q by 2, or is it q, sorry, or is it, sorry, none of the above? None of the above. What do you think it is? I want to see the spam in the chat box. What do you think it is going to be? A very, very interesting question. Where are the charges distributed on the plates of a capacitor or on the conductors? Is it the inner side? Is it the outer side? Or is it distributed equally on the inner outer side? Or is it something else only? It's something different, sir. It's none of these at all. Okay. I want to see all your answers, guys. Come on, in the chat box right now. 3C. Most of you saying 3. Third one. Kanika saying B. Soumya saying 3. Okay. Tom saying C option. Well, let me tell you, the correct answer for this particular question is answer B. Is basically answer B. No, it is not A, it is not C, nor is it D. It is answer A. So this thing comes from the logic of Gauss's law and the plate problems, which we have dealt before. See, whenever you have two or more plates and you want to find what are the charges like. For example, this is a charge Q. Let's say this is 3Q. These are plate problems. What you do is first find the total charge. The total charge is basically Q plus 3Q. Then you take the total charge divided by 2, which is basically the number 4Q divided by 2, which is 2Q. This 2Q is always on the outer plates. This 2Q is always on the outer plates. That means if I draw the second step, I will show that there is a 2Q charge here and then there is a 2Q charge here. Now, what about the inner side? Well, use charge conservation. Now use charge conservation. Now use the charge conservation concept. So according to the charge conservation, on the left plate, the total charge must be Q. So if there is 2Q here, obviously there must be minus Q charge over here. Does that make sense? 2Q minus Q is Q. Now over here, if there is 3Q charge, 2Q plus Q will give you 3Q. So this side will have a Q charge. That's it. So this is the charge distribution on the plates. 2Q minus Q, Q and 2Q. That's the logic for finding the charge distribution. The outermost sides will get equally distributed and the inner sides automatically adjust to compensate for the charge conservation. Okay, so now think similar logic if I tell you that, hey, listen, there is a Q charge here and there is a negative charge on the right plate. What would be the total charge? What would be the total charge? It will be Q plus negative Q. So which is nothing but 0. So when I say the total charge divided by 2, it will be 0 by 2, which is just 0. Hence, what will happen? Hence, what will happen? Think about it. There is no charge at all outside. So 0 charge outside, 0 charge outside. Now conserve the charge, conserve the charge, conserve the charge. So if total charge was nothing is there outside, entire charge will be here. Nothing was there outside, so entire charge will be here. So Q and minus Q, as simple as that. Q and minus Q, as simple as that. Does that make sense now? So did point 2 and 3 mean the plates itself, not the gap between the plates? Yes, it meant the side of the plates, the inner side. See, if you take any, let's say for example, I will take this book only, Tattva book. Okay, so imagine this is that plate. So this side is side number 2 and this side is side number 1. Which side of the plate are we talking about? Okay, so that was 1 and 2 or 3 and 4. Inner side, outer side, so on and so forth. Now clear? This is how the charge distribution occurs. I bet many of you did not know about this. Now, based on that, there was a level 3 question, JEE advanced question. See, This is where people go wrong, or this is where people make mistakes. Say, for example, the potential difference is 10 volts and distribution of charge is as follows. The left plate, the left plate is given, for example, 3 coulomb, and the right plate, for example, is given, say, I don't know, maybe minus 7 coulomb. Some random values I have taken, 3 coulomb and minus 7 coulomb. Now, the question is, find find the capacitance. Find the capacitance. This is a very good level question. Many people will go wrong about it, I bet. Okay. So you will be like, sir, wait a minute. Can't I just use Q is equal to CV? I'll be like, okay, fine, use Q is equal to CV. Okay. Capacitance, I do not know. Voltage, potential difference is 10, sir. Okay, 10. What is the charge? Will you put 3? Will you put minus 7? Or will you put something else? What is your answer for that? Now you are stuck because, sir, you told charge is plus q minus q. We thought it is like that only, but now here the charges are only unequal. So what to do now, sir? Don't worry, Shreyas Sir is here for your rescue. So now just do one simple thing. What is the total charge? Just calculate it. What is the total charge? Just calculate it. It is nothing but 3 plus negative 7, which is nothing but minus 4. Is that right? It is nothing but minus 4. Everybody with me? Now, what you do is find the total charge divided by 2, which is minus 4 divided by 2, which is basically minus 2. Now, what you do is put that minus 2 charge outside. Where will you put that minus 2 charge, my dear warriors? My dear lions, where are you going to put it? Outside. So, let's put it outside. So, minus 2 over here, minus 2 over here. Okay, so this is minus 2 coulombs. Remember that. Minus 2 coulombs. This is minus 2 coulombs. You have to conserve the charge, obviously. Conserve the charge. So to conserve the charge, what will be the charges on the inner side? Just check that out. Minus 2 plus what will give you 3? Minus 2 plus which charge will give you 3 coulombs? Minus 2 plus 5 obviously gives you 3 coulombs. So there will be plus 5 over here. Plus 5 coulombs over here. Similarly, minus 2 with what charge will give you minus 7? Obviously, nothing but minus 5 coulombs. So minus 5 minus 2 gives you minus 7. Charge has to be conserved. Okay, what next, sir? Now, see, always these outer charges, ignore that. The energy is stored inside the capacitor. In fact, the electric field, everything is over here. The electric field, everything is stored here. This is where the energy is stored. This is where the energy is stored in a capacitor between the plates. Between the plates. So what charge do you consider? Just look over here. This outer charge was 0. You never bothered about it. You are only bothered about this because the field is because of these two charges. The field is there between these two plates. Everything is stored in between these two plates. So this is the charge which you should consider, my dear students. Hence the charge on the capacitor is 5. Hence the charge on the capacitor is 5. Hence the capacitance that one will get will be 5 divided by 10. Therefore, the capacitance is 0.5 farad. Capacitance is 0.5 farad. Got it? How to solve these questions? Yes. Srinidhi, try to solve those questions on your own. And let me tell you, kinematics is a huge chapter. So when you said you solved 50 questions, 50 is actually a small number. 50 is actually a small number for considering kinematics in 1D, 2D and relative. So actually you should solve 100 to 150 problems and solve easy questions, at least 70 to 80 first, then go to medium 50 questions, then go for 30, 40 hard questions. That's how you will increase your level. Okay, fair enough. So these are all interesting concepts. So now let's go to the calculation of the capacitance. It's very straightforward and let's talk about it. First, let's go to parallel type of capacitor. Then we will go to the cylindrical type. Now, first of all, when we talk about a parallel plate capacitor, meaning two parallel planes. So it will be something like this. So I'm just showing using Tattva books over here. So imagine two plates in front of each other. That's it. They are just two plates in front of each other. The cover pages which you see, these two cover pages are the ones which hold the charge. The back covers, the back pages, they do not hold any charge. The back sides do not hold any charge. The front sides hold the charges. One is positive, one is negative. Okay, the energy is stored between the empty space, between this empty space which you see between these two plates, and there is electric field also in between them. All right, there is some distance between the plates, there is some area of the plates, there is charge q, there is electric field. Using these quantities only we'll be able to figure it out. Okay, so here is what we are going to do, my dear students. First of all, let me recollect this formula. When you have a charged sheet, when you have a charged sheet, charged plane, then the electric field goes here also, and it goes here also, and that electric field is given by sigma by 2 epsilon naught. Why the 2? Because it is going two sides. But when you have a charged conductor surface, remember that. So it's a charged conducting surface. So this is probably the surface of a conductor. Probably this is the inner side. This is the solid part maybe. So think of it like that. So maybe this is the inner side of that particular conductor, something like this. Okay. Then the electric field will not be inside. Remember, electric field lines are only going to be outside, and then it is just given by sigma by epsilon naught. Electric field inside is always 0. It is only going one side, so that number 1 is there. When it goes both the sides, then you will see that the number 2 will be there. That's how I remember, and in fact, that's how I made you remember it. Right? That is how it is. That is how it is. Warrior Whitey, obviously, when you study for JEE, you are studying for CBSE, State Board, EMSAT, KCET, COMEDK, everything you are studying. How is it possible that you are studying for JEE and you cannot study for CBSE? It is automatically covered, right? But if you are studying for CBSE, you are not studying for JEE. I understand that. It is not vice versa. That is the reason why you see many students who do well in JEE, automatically without much of effort, they do well in boards also. It's a natural thing. Now, when I look over here, these are also conductors. These are also conductors. So this is the surface of a conductor. So directly, I can say that the electric field which is there between the plates, directly I can say the electric field which is there between the plates, I can directly say it is nothing but sigma by epsilon. Sigma by epsilon, where that sigma is the surface charge density, which is nothing but the charge which is there on any one of the plates. You can take Q, okay? You can take, let's say, this one, or you can take this one, doesn't matter. Let's say I take this one. How much charge is there on this particular plate? It is nothing but Q. So it is Q by how much area? A. So hence it will just be Q by A epsilon naught. That is the electric field's value. Directly I can give it. This is one way. But the other way is, you look at the plane of this charge and you look at this plane of the charge and you think like this, that this charge on this plane gives electric field both ways. This charge in this plane gives electric field both ways. And to explain that point further, I'll show you the diagram. Imagine this is one side of the plane. Electric field is going like this as well as like this. Electric field is going like this as well as like this. Okay. And you consider the other plane of the charge, which is over here, let's say for example, and it's negative. So electric field will be pointing inwards. Do not forget, electric field has to point inwards like this. Electric field goes like this, and like this. And the interesting thing you see is in the between also, where you will notice that the pink and the light blue lines, they are actually in the same direction in between. Can you see that, my dear warriors? In between, this is one plane of charge, this is another plane of charge. In between the plates, the lines are in the same direction. That means they add. Whereas here, one is this way, one is other way. One is this way, one is other way. Observe it carefully. The pink line and the blue line, they are opposite. That means they cancel. That means they basically cancel out. Hence, the electric field outside is zero. Hence, the electric field in this outside region is zero. The electric field only inside this region, the electric field adds up, and each of this electric field, because this was a plane of charge, a charged plane gives sigma by 2 epsilon naught field. So each one of this is sigma by 2 epsilon. Even the pink one is also sigma by 2 epsilon. Hence, when I try to calculate the net electric field which is there inside, it will be sigma by 2 epsilon naught plus the sigma by 2 epsilon naught because of this pink charges, and both of them will add up, and hence again I will get sigma by epsilon, which is same as over here. Hence I will get the same answer, which is q by a epsilon naught. That is again the electric field which is there inside. Whether you go via this method or this method, the answer which you get is the same. That's what I wanted you to see. So this was method 1. This is method 2. And let me remind you why I'm doing this is because many students do not know the true significance of how these things come, and they get confused when a tricky question comes. Okay, so that is the reason why I explained you. When you have a plane charge, that plane charge will give electric field both sides, right? It will give both sides. Remember that. Anyways, and it is sigma by 2 epsilon. But when you take a charge on the conductor, it is giving electric field on one side. So you use the formula sigma by 2 epsilon. So when you solve this problem, either you can consider these charges to be on the surface of a conductor, then you use directly this formula, or you consider these charges as the plane, consider these charges as the different planes, and you find the net electric field between them. It's one and the same thing. Okay, current electricity lecture 2 after this, LOL. Okay, I hope till this point everything is absolutely very clear. Now, once I get this, I will proceed to the next step. I'll proceed to the next step. I just got electric field is Q by A epsilon naught. Now, if I write Q, how much it is? If I write Q, how much it is? A epsilon naught will go on the top with E. So it will be A epsilon naught multiplied by E. That's what I will get. Can I write the electric field in terms of something else? I think we can. This electric field is related to the voltage difference also. Remember, there will be some voltage difference. Potential difference will also be there. And how is electric field related to the potential difference? We all know dV by dr is with a negative sign the electric field. But if I look at it magnitude wise and for a uniform electric field, I can just say delta V by delta R is E magnitude on an average, considering it is uniform electric field. Why is it uniform? Because the lines are parallel. How much is the voltage difference? It is V. How much is the gap between these 2 points? It is the distance between the plates. Hence, it is E. Oh, so E is nothing but V by D. So why not put V by D over here? Next step, I'll just rearrange everything. So I will get Q is equal to A epsilon naught divided by D into V. But wait a minute, compare it. Compare this with, compare it with Q is equal to C into V. Q is equal to C into V. Clearly, clearly whatever is there over here is the capacitance. Whatever is there here is the capacitance. Therefore, the capacitance is A epsilon naught divided by D. Capacitance is A epsilon naught divided by D, and that is what I will put over here. So the capacitance of a parallel plate capacitor is A times epsilon naught divided by D. Later on, this epsilon naught will be replaced with just epsilon of the medium, and you remember epsilon of the medium in between is permittivity of vacuum into that K, which is your dielectric constant, which we have studied before, in the chapter of electrostatics. Every medium has its own dielectric constant, and that dielectric constant can be substituted here. We'll talk more about dielectrics in a bit, but right now, just remember, it is just the permittivity of the medium. But if it is vacuum, then no need of putting K. You can just put epsilon naught A divided by D. So that's the formula. That's the formula. Till this point, is everybody clear? Till this particular point, is everybody clear? Give me a thumbs up quickly, guys. Yeah. Wow, physics is world. You are a class 10 student finishing 11th standard syllabus and doing 12th now. Any suggestions? Continue what you are doing. It is perfect. I mean, by the time you reach class 11th, you would have done with the syllabus, and then you can concentrate more on Olympiads. So I would suggest give lots of Olympiads and also take part in all the events which will go on in your school and college, because you would have completed the syllabus. You won't have the same tension as the other 11th and 12th standard students. So take part in whatever debates, or maybe some competition is there, maybe some Olympiad is there, maybe some, I don't know. So take part in that. That will improve your personality. At the same time, just revise all the theory, revise all the problems, keep solving many questions, PYQs. That will keep you in touch with the subject. So when the actual examination day comes in your 12th standard, you ace it. And at the same time, you have a very good personality at the same time, and overall development. That is what I would suggest. Yes. So moving on to the next one. Moving on to the next concept now. Okay, actually, let this be there. Now, this concept of force between the plates of a capacitor, which somebody was already asking. Sir, won't the plates or the conductors, because they are oppositely charged, won't they attract, sir? Obviously, they will attract. Sir, who is holding them? See, they are enclosed in some shell or some body. Like, for example, when I showed you the photograph of a capacitor, I showed you there is some casing, there is some shell, there is some uh, you know uh, uh, fixture or some body which is holding it. So that body holds the plates of the capacitor and prevents it from sticking it to each other. Obviously, nobody was holding it, it was floating in air. It would have gone and stuck to each other like magnets. So that is not happening because you're holding it because of the casing or the enclosure which is there. But what is the force on the plates of a capacitor? How do I find that out? Okay. So first of all, if there is a positive and negative charge, to find the force, I can use this concept. Force of attraction. Let's say I put it over here like this. Between them will be like this. So the force of attraction or repulsion will be, the charge will be there on both the plates. Let's say this has plus Q, this has minus Q. We are just talking about the magnitude now, not about the direction. It's understood it is attractive. Is charge multiplied by the field. Multiplied by the field. Now, I'm deliberately going to do something wrong over here. Observe what I'm doing wrong. Okay, and you tell me. Electric field. Sir, you already gave the formula, sir. Electric field. Where is it, sir? Here. Q by A epsilon naught. Okay, perfect. So why not put the electric field as Q by A epsilon naught? And then the answer will be Q square by A epsilon naught. That is what the force will be. But like I said, I'm deliberately doing it wrong. This is not correct. This is having some mistake. What is that mistake? Can you identify? Is the question. This is wrong. Why is this wrong? Is not because Q is wrong. It's because E is wrong. Like, why, sir? E is wrong, sir. You just gave the formula, sir. Over here only, you told electric field between the plates of a capacitor is Q by epsilon naught. Okay. So I have a question for you. I have a question for you. Imagine there is a positive charge. Imagine there is a negative charge. Just take some example. When I want to find the force on this example, this negative charge, and I write it charge into the field, charge is whatever this charge is. Okay. This field, this field is the field due to which field? Which charge? Positive or both? Answer in the chat box. Answer in the chat box. What is this field? Remember, if this particular charge, it does not matter whether it is positive or negative also, guys, just take any example. Imagine there is a charge capital Q over here. Imagine there is a charge small q over here, and I want to find the force on this charge. That force on this charge is the charge multiplied by the field. This field is due to whom? Due to Q only. Due to Q only. Remember that. It is only because of Q. This is external field. This is external field on that small q charge. On that small q charge. It's not because of that charge itself. So, understand over here, when I wrote this field as q by a epsilon naught, I hope you remember, we calculated it because of this as well as this. Both their contributions were there. So, I need to only consider one of their contributions, either due to this side or due to this side, basically field due to the other set of charges. If I'm considering the force on the negative charge, it will be the field due to these acting on it. If I consider the force on the positive charge, the force on it will be charge multiplied by the field due to the negative charge, which is the pink one. So either you consider this or this, not both, because you're finding the force on one of the other. So that is the reason why you will see that this field over here is due to other plate. And when I say due to other plate, it is not q by a epsilon naught. It is not q by a epsilon naught. It is nothing but q by 2a epsilon naught. Q by 2a epsilon naught. And I'll again mention that over here, just so that you are clear. This will give out electric field like this. This will give out electric field like this. And when you consider the charges over here on the other plate, which is, let's say, for example, q or minus q, then the force acting on it, then the force acting on it is the charge multiplied by this particular field due to this one, which is nothing but sigma by 2 epsilon naught. So that is why the 2 will come, and hence the final answer for this question, will be q square by 2a epsilon naught. This is the answer for this. Is that absolutely clear, my dear warriors? Yep, q square by 2a epsilon naught. Now, there are questions where I have also seen in between the plates of a capacitor, they will tell you, listen, there is a proton or an electron. For example, there is a proton which has a charge of plus E. Then, what is the force on that proton? Or that electron, or that alpha particle, or that beta particle? Those kind of questions can be there. Maybe they will ask you to use some kinematic equations also. Why not? Force is there, acceleration is there, velocity will be there, displacement will be there. So you can use kinetic equations also. But before going to that, what is the force on it? Now you'll be like, sir, should I use this formula directly? Force between the plates? Exactly no. Because this is the force between the plates of the capacitor, not the force on a third particle. So when I want to find the force on a third particle like this, and I write it down over here, say for example, the force on this particular particle is F, It will depend on the net electric field, because now even these positive charges and these negative charges will together attract or repel this proton, electron, alpha particle, beta particle, whatever it is. So this electric field which I will consider will be the net electric field. So hence the force will be whatever is the charge on that particular particle multiplied by the electric field. This is due to both the plates. Due to both the plates, that means it must be Q by A epsilon naught. Keep this in mind. Okay, it is because of both the plates. It is because of both the plates. So you put Q over here, and this is our force. If you want to find acceleration, that will be force divided by the mass. So it will just be Q divided by that mass, whatever is there of that particular charge, multiplied by Q and divided by A epsilon naught. All these numbers are constant. That means even the acceleration is going to be constant. And once the acceleration is constant, it also means you can use kinematic equations. Kinematic equations are allowed. Kinematic equations are allowed because acceleration is constant. Got it, my dear warriors? Okay, so now you know the clear-cut difference between what is the electric field between the plates of a capacitor. How is it found? In fact, two methods are there. And you now know what is the electric field due to any one of the plates of the capacitor, which can be used to find the force between them, which is this one. But when you have to find the force on a third particle, then you use the total electric field acting on that third particle kept in between. Yeah. I hope this is clear. PYQs plus mocks is enough for JEE Mains physics. Pujari, how many PYQs will you solve? Will you solve all the 10-year PYQs? If you solve that, probably even decently enough, because every year there are some 2 or 3 attempts. Some years there are 4 attempts also. Each attempt has some 6 to 10 or 12 shifts, and then so many questions. If we practice, it is decently good only. There is nothing wrong, because right now JEE is at an advantage of having so many collection of good questions. So solve those PYQs, go with the NCERT exercises also, and obviously the concepts are needed at the end of the day. So just don't solve PYQs, you will need the concepts also. Okay, now that you have understood till this point, let's take 2 cases of parallel plate capacitor, which is often asked in many of the questions, where you take a capacitor and connect it to a battery and then do something. Maybe you are increasing the area, or maybe you are bringing the plates close, or maybe you are doing something with the medium. And the 2 cases are once when the battery is connected and once when the battery is not connected. See, if we take a capacitor and connect it to a battery, what will the battery do? That battery will ensure that there is a voltage difference between the plates of the capacitor. So when the battery is connected to the capacitor, what is it that remains unchanged? It's the voltage provided by the battery. That means the potential difference between the plates of a capacitor remains constant. But the charge may not remain constant. The capacitance may change if you change the distance or change the area of the plates, because you just saw that the capacitance completely depends on the area and the distance between the plates. Okay. What if you are not connecting only anything? Then what will remain constant? Think logically. The plates are not connected to anything. Nothing can go out, nothing can enter in. At least when the battery was there, the battery could supply some charge. Now, because there is nothing to supply or take that charge, what remains constant is the charge. So it's the charge which remains constant when the battery is removed. When battery remains connected, it's voltage which remains constant. Perfect. Now, different things, and let's see what happens on each of them. Pujari, 6 years is okay, but I would suggest 10 years, because last couple of years the papers have been simple. So just to prepare for the worst of the worst, I would say solve some old papers also. So when I said 10 years need not be exactly the last 10, pull out some 1990s, 1980s paper, suddenly pull out some screening paper. So solve some variety, because you cannot expect the paper to be as simple as last year. Something goes wrong, you need to be prepared, or else you will be only able to solve the easy questions in the paper. And if some hard questions are there, you will completely leave them out. So practice a mix of PYQs, just not the last year PYQs. But 6 years, what you are solving is very good. Push it harder, solve some other PYQs also. Okay. All right. So let's take both the cases: battery connected, battery removed. Say, for example, the distance between the plates is changed, then the area is changed. Okay. I will see what happens to the charge, the capacitance, the voltage, and the electric field. Okay, let's have a look, guys. What happens in either of the cases? Let's see what happens in either of the cases. So the distance between the plates is increased, area of the plates is increased. What do you think happens when the battery is removed? Battery is removed, the charge can't go anywhere. So what happens, my dear warriors? The charge has to remain constant. It will not change at all. So no change, or rather, I would just put the word constant. I just put the word constant over here. What about the capacitance? Well, capacitance formula, if you remember, is nothing but epsilon naught A divided by D. If somebody increases the distance, what will happen? Think about it. If somebody increases the distance, denominator increases, the ratio will reduce. So hence the capacitance will reduce. Capacitance will reduce. What will happen if somebody increases the area? Then the numerator increases, thereby increasing the ratio. Hence the capacitor will increase its capacitance. Perfect. Awesome. Awesome. Now, next, what about the voltage? Well, we all know that Q is equal to C into V. Q is a constant. Q did not change. So if capacitance increases, voltage decreases. And if capacitance decreases, voltage increases. So it is inversely related to each other. So hence, here if capacitance is decreasing, voltage will increase. Here if capacitance is increasing, voltage will decrease. Exactly inversely proportional to each other, because charge is remaining constant. Now you will be like, sir, what about the electric field? Well, let's think about it. Is there a formula for electric field? Electric field is voltage difference divided by the distance. Voltage difference divided by the distance. Or you can also use Q by A epsilon naught. Any one of these formulas is okay. Because charge is a constant, I feel it is beneficial for me to use this formula, because Q will be a constant. Or else voltage is changing, D is changing, might be little bit confusing for me. Hence, I'll use the second formula. Let's see what happens. In the first case, distance is changing. Distance is not even there in this formula. It's not even there in this formula. Charge is constant, A is constant, epsilon is constant. So hence, what will happen? The electric field will remain the same. It will remain the same. When area is increased, I think things will change now. If area is increased, well, charge will not change, epsilon will not change, area increases, ratio will go down, field will go down. Hence, the answer will be the field reduces. Hence, the field will reduce. Is that absolutely clear? Everybody with me? All right. Cengage JEE Advanced is enough for JEE Advanced preparation. Guru F, definitely not. Nothing is enough like that. Okay. uh, you have to practice more books. There is Ekalavya material available. I'll show you that there is a link probably in the description box, or if it is not there, put a comment after the video. I'll share with you unseen questions, very different questions, which is used by Ekalavya students who pass every year to get into IIT. It's the collection of those problems for physics, chemistry, maths. So that module is like that, that rankers module, which you say for sure short JEE advanced selection. So solve that, number one. Number two, JEE advanced PYQs. Very, very important. All the PYQs. When battery remains connected, again the same thing will do. Again the same thing will do. Distance is increased, area is increased. Let's see what happens to the charge. For here, because battery is connected, voltage will remain constant. Then we'll go to probably capacitance, and then we'll go to the charge, and then we'll go to the electric field. Let's see what happens in each of these cases. Okay, just like over here, we'll solve this. First of all, because battery remains connected, doesn't matter what happens here, it will be a constant. It will be just a constant. That is obvious. Capacitance. Well, capacitance is epsilon naught A by D. Capacitance is epsilon naught A divided by D. So if distance increases, capacitance will decrease. If area increases, numerator increases, capacitance increases. Charge is CV. So let's use that formula. Q is equal to C into V. As we can notice over here, voltage is not changing. So if capacitance increases, charge also increases. If capacitance decreases, charge also linearly decreases. So whatever happens with capacitance, same thing happens with charge also. This goes down, this goes down, this goes up, this goes up. Perfect. What about electric field? Now charge is changing, so I will not stick with that charge formula. In the one, if you remember, we used this formula, not this formula, because it was convenient. Now I feel I have both the options. One option is I can use voltage by distance, or I can also use Q by 2A epsilon naught. But I feel I will not use this, I will use this now, because voltage is constant. That is the reason why I'll use this. So distance, if it is increasing, E will decrease. So naturally, E will reduce. Perfect. Here, area is changing, doesn't matter. I'm not looking at that formula, looking at this formula. Neither voltage changed nor the distance changed. So it will definitely remain the same. That's how you solve those questions where area, distance, etc. is manipulated and you're finding its effect on the charge, capacitance, field, or voltages. Is that absolutely clear, my dear warriors? Perfect. Chalo. Let's move on to some questions. The parallel plate capacitor is charged if the plates are pulled apart. Well, a parallel plate capacitor is charged. I think I showed the answer by mistake. If the plates are pulled apart, that means the distance increases. That means the capacitance will decrease because capacitance is epsilon naught A by D. If capacitance decreases, what will happen? A capacitor is charged. It's not connected to anything. So here the charge is basically constant. The charge is basically constant. So what will happen? Q is equal to CV. C is inversely proportional to voltage. Capacitance reduces, so voltage will increase. So potential difference between the plates will increase. Potential difference will increase. As simple as that. Cool. Let's move on to the next question on your screen. A capacitor, one of the two plates is 2, other is 4. The potential difference developed across the plates of the capacitor is how much? Okay, let's have a look. This is one plate, this is another plate, this is plus 2, this is plus 4. Capacitance is given, voltage is asked. Okay, we all know the formula Q is equal to CV. Charge, I don't know. Capacitance, 1 micro. Voltage, I don't know. How do I find the charge? Our logic, which I gave you before. Find the total charge. What is the total charge? 2 plus 4, which is basically 6. Now do total divided by 2, which is 6 by 2, which is basically 3. So plus 3 here, plus 3 here. Use charge conservation and find the remaining. If plus 3 is here, minus 1 will be here. 3 minus 1 is 2. And 3 plus 1 is 4. So here it is plus 1. So the charge on the capacitor is basically 1. It is basically 1 microcoulomb. Micro will cancel. Micro will cancel. So voltage will be nothing but 1 volt. 1 volt, which is option number B. Option number B is the correct answer. Is that clear? Yep. Yes, Bharadwaj, you are quite late. Missed a couple of concepts, and I feel you should watch it from the start, unless you have read this chapter before or understood this chapter before and coming here for revision. Okay, so I would suggest you watch it from the beginning, and you can even watch a live session from the beginning. That facility is there on YouTube. Voltage rating of a capacitor is 500 volt. A dielectric can withstand a maximum field of this much. The plate area is this much. What is the dielectric constant of the capacitance? If the constant if the capacitance is 15 picofarad. Okay, let's understand it. Is the formula for parallel plate capacitor given to me? Yes, it was epsilon naught K A divided by D. All right. Now, uh, what is the dielectric constant if the capacitance is 15 picofarad? Plate area is given. Uh, Voltage rating of the parallel plate capacitor is given. Okay. And maximum electric field which it can withstand is also given to me. Area is also given to me. Now, in such cases, think about it carefully. What is the approach that you will use? What is the approach that you will use? Using this particular piece of information, since I know that the maximum electric field which it can hold, because after that maybe it breaks down, maybe something happens, it burns, is given to me. Electric field is the voltage upon that distance, voltage upon that basically distance. This is given to be 10 to the power 6. This delta V is given to be basically 500. This delta R is the distance between the plates of a capacitor. So what will D be equal to? Two zeros cancel and I'll get 5 into 10 to the power minus 4 meters. That is the distance between the plates. Now substitute that D here. C is given, everything else is given. You will get the answer. What's the capacitance? The capacitance is 15 pico. Pico is 10 to the power minus 9. What is epsilon naught? It is 8.86 10 to the power minus 12. K unknown. Area 10 to the power minus 4. Whole thing divided by this distance value, which is 5 into 10 to the power minus 4. Now you can see the only unknown over here is this number K. So solving this, you will get the value of K. Solving this, you will get the value of K. Okay, so you solve this, I think you will get the answer of K as 8.5. You will get the answer as 8.5. That is the answer. Yep. Clear? So we had to use two different formulas. This information was needed so that I could solve it for finding the unknown distance between the plates. Otherwise, this information was not needed if D was already given. It was given only for a particular reason. Cool? I hope that is understood. Let's move on now to the cylindrical type and the spherical type. In case of cylindrical type, you have two concentric cylinders. One cylinder is positive, one cylinder is negative. The electric field goes from positive to the negativeness, and you will see there is energy which is stored in the space of that capacitor. Using the same logic of derivation not needed, not important, but you will get the value of a cylindrical capacitor, where A is the inner radius, inner cylinder radius. B is nothing but your outer cylinder radius. H is, or L is over here. L is basically the height of the cylinder. Height of the cylinder. You will notice that the capacitance formula comes out to be 2 pi epsilon naught L divided by log of big by small. Big is B, small is A. Ln B by A. This is the value of the capacitance of a cylindrical type of capacitor. Cylindrical type of capacitor. Please remember one important thing. Again, I'll show it to you over here. Say for example, this is the inner cylinder. Let's say this is the outer cylinder. Please remember some small things over here. Innermost side has no charge. Same thing, outermost side has no charge. This side, if it has plus Q charge, this side will have minus Q charge. The charges are only there on the inner side. So charges on inner surfaces only. Charges are on the inner surfaces only. And hence you will see that the electric field is also between the inner sides, from the inner side of this to the inner side of the outer one. So the electric field is also here. So naturally, if you count what is the electric field here, it will be 0. Electric field over here is also 0. Electric field here is also 0. So the electric field only exists in that gap which is there in that cylinder. In that gap which is there in the cylinder. It is a radial electric field. It is a radial electric field. It is not constant like parallel plate capacitor. Okay. I hope this is clear. All right. All right. Moving on to the next type of capacitor, which is a spherical type. Obviously, spherical type means two concentric spheres need to be there. Inner sphere can be positive or negative. Outer sphere can be again oppositely charged. Electric field will only exist in that gap. Outer side there is no charge nor field. So charges on inner surfaces only. Charges are on the inner surfaces only. And also the electric field is between inner surfaces. Between the inner surfaces. If somebody checks also what is the electric field here, it will be 0. Electric field here will be 0. Only in between there will be electric field. So what's the formula for that capacitance? What's the formula for that capacitance? Again, if I tell you A is nothing but inner spheres or inner radius, and let's say B is outer radius, B is basically outer radius, then the formula for the capacitance looks something like this. It is 4 pi epsilon naught 1 by A minus 1 by B. This is the formula for the spherical type. 1 by A minus 1 by B is in the denominator. So now we have seen all the three formulas, whether it be parallel or cylindrical or anything else. For parallel plate, it is epsilon naught A divided by D. There is no pi in that case because pi is only associated with circles. So here there is no pi. So epsilon naught A by D is for parallel plate. For cylindrical plate capacitors, it is 2 pi. That pi came because of that circle which is involved. So 2 pi epsilon naught length divided by log. So cylinders have log. Remember that. And lastly, you have spherical type, which is 4 pi epsilon naught because it's a 3-dimension. So 4 pi came because of the sphere. So 1 by A minus 1 by B. That is the formula for it. If you remember this much, it will help you a lot for solving many questions. Okay, fair enough, guys. Shall we go ahead? Now, there is one more special type of capacitor, and that is called as an isolated spherical capacitor. Why this? Let me tell you. Imagine there was a positively charged sphere and then there is a negatively charged sphere, something like this. Negatively charged sphere, something like this. So this one is positive. This one is positive. This is negative. So you will see that the electric fields will go from this to this. Electric field will go from this to this. Now imagine I make that outer cylinder little bit huge. I make it little bit huge. Again, this is positive, this is negative. You will again see, okay, fair enough. Electric fields will go from here to here. I make it even more huge, in fact, so huge that it does not exist only. Then what will happen? Think about it. Okay, just imagine you just have one sphere. Imagine positively charged. It could be negative also. The electric field lines go with the hope they will meet a negative charge, but to their surprise, it never comes, but they do not know. We just tell them politely, listen, you will find the other side of the sphere or the negative side at infinity. So remember, infinity means mathematical or mathematically polite way of saying never. Like if Champa is asked by Pandu asks Champa, when will I meet you again? Champa mathematically replies, limit extends to infinity. Pandu will think, oh, Champa is a very smart girl. She is my life partner and she gave a mathematical answer. But once he studies limits in JEE, he will understand Champa politely said, I will never meet you again. So, same thing over here. these field lines will endlessly go till infinity. Till infinity. That means the outer shell, the outer radius is basically infinity. Wow. So our original capacitance formula which was there, which was 4 pi epsilon naught 1 by, let's say this radius I call it as r, this radius I call it as r. And the formula, remember, was 1 by a minus 1 by b. So how about using it? A is nothing but r, b is nothing but infinity. So I will get it as 4 pi epsilon naught. 1 by r is there. 1 by infinity is 0. Limit 1 by infinity is 0. So 1 by r minus 0 is 1 by r only. So it is just 4 pi epsilon naught 1 by r. So take it on the top. So capacitance will become 4 pi epsilon naught r. R goes on the top, 4 pi epsilon naught r. I hope it is understood properly. So the capacitance of a single sphere is also there, with the hope that the other side of the sphere or the other shell is present at infinity, which is politely saying no. So that is also going to behave like a capacitance whose value is given by 4 pi epsilon naught r. Again, a very, very important formula for isolated spherical capacitor. Now, based on this, there could be some amazing questions like the one over here. Find the capacitance of Earth. Wow, what a question it is. But the reason I can't give a specific planner right now is because on YouTube, things are very dynamic, bacha, honestly speaking. Because if I tell you something, pakka this week I'll do this. If it doesn't happen because things keep changing, it will not look good. But I'll tell you a tentative plan that my plan is to complete everything as much as possible by September. And we are doing parallelly 12th and 11th, but major focus will be on 12th, and 11th we'll do all the important stuff first. That is what we are going to do. Okay, so mechanics I will be covering properly parallelly, and after current electricity, capacitors will be going on to magnetism. Ray optics is already done. So once magnetism is done, again probably we'll push 11th standard syllabus till the end, like the mechanics part, rotation, momentum, collisions, everything, and then we will move on to wave optics and all those things. And just before doing wave optics, I'll make sure that I'll teach you SHM and all those stuff of 11th standard, so it becomes easy for you to understand waves. And then we will complete modern physics. That's the plan. Okay, all right. Capacitance of Earth. Earth is like an isolated spherical capacitance. So capacitance is 4 pi epsilon naught r, which is 1 divided by 1 by 4 pi epsilon naught into r. Reason for doing it, this number I know is 9 into 10 to the power 9. 9 into 10 to the power 9. Radius of the earth 6.4 into 10 to the power 6 meters. So just do the math and see how much do you get. Yep. So comes out close to 7.1 into 10 to the power minus 4. 7.1 into 10 to the power minus 4. So it's like probably saying 0.71 millifarad. 0.71 millifarad. And that too for Earth, you took such a big planet and then you measured its capacitance and still it came out to be 0.71 millifarad. That's why I said farad is a huge unit. So don't expect you getting farads of capacitance. Very difficult to achieve, but it can be achieved. It's not impossible. Yeah. And typically the capacitors you get in your day-to-day life are in pico or even in nanofarads. Exactly. Yep. Yes, it is too less. That's what I was telling you. How about this one? This is a very interesting question, I guess. 8 drops of mercury of equal radius possessing equal charges combine to form a big drop. Find the new capacitance of the big drop. Compare it to the each individual small drop. Let's try to analyze this. If you take a small drop having some radius r, the capacitance of that small drop let's say I call it as C naught, will be 4 pi epsilon naught small r. But now what you are doing is basically you are taking how many such drops? 8 of them. So you multiply such 8 drops to find the new bigger drops volume and hence the radius. Imagine this is that big drop. Imagine this is that big drop having some new radius. This guy's volume will be 4 by 3 pi small r cube. This is nothing but the volume. You multiply the volume by the number 8 because it is clearly mentioned 8 drops were there. You will get the volume of the big drop. How much will it be? 4 by 3 pi capital R cube. 4 by 3 pi, 4 by 3 pi just cancels. I hope you are able to see that. 4 by 3 pi, 4 by 3 pi just got cancelled. So what do I get over here then? What do I get over here? Let's see. Here R cube is there, here 8 is there. So capital R cube is basically 8 times small r cube. Therefore, R will be cube root of 8 is 2. So 2 times of R. So the big radius is double the small radius, which means the new capacitance, which would be 4 pi epsilon naught into R, that R itself being 2 times of small r. Remember, I can write 4 pi epsilon naught into small r on one side, and let me just put that number 2 over here. This number 4 pi epsilon naught r was the original capacitance, if you recollect it. That's it. So the new capacitance is the old capacitance multiplied by 2 times. So hence the answer will be 2 times. Hence the answer will be 2 times. Option C. Fair enough? Yep. If you talk about the charge on it, mind it, it will not be 2 times. It will not be 2 times. Think why? Because the charges will also get multiplied 8 times. Charges will also get multiplied 8 times. So if I were to do that problem for the charge, if this had a charge of Q and I will multiply it by 8, so the new charge on it, capital Q, will be 8 times of Q, will be 8 times of Q. What about the voltage? What about the potential? Will the potential remain the same? No, right? Potential will also change. I know it is not asked, but in case it was asked, think about it. Original voltage will be K small q divided by small r. The final voltage, or don't even have to do this. We know that this Q is equal to that new capacitance into that new voltage. New capacitance into new voltage. This capital Q is nothing but 8 times of small q. This C is 2 times of the original capacitance. So we also know one more thing. Okay, by the way, 2 and 8 cancel, so it will become 4q by C naught is equal to V. What is q by C naught? Charge by capacitance. Charge by capacitance is nothing but the original voltage. So 4 times of the original voltage is the new voltage. 4 times of the old voltage is the new voltage. 4 times. As simple as that. So you can use all these things for solving the problems. It could be on charge, it could be on voltage, or it could be on capacitance. It could be anything. So that is how you do these questions. Now what about the energy stored in the capacitor? Very interesting question. Energy stored in a capacitor. Beautiful concept, guys. Let's try to understand it. Obviously, the energy is stored between the plates of a capacitor. If there was no charge, there would be no energy. But when it is completely charged, there is energy stored. So while charging, I add a charge slowly, dq, dq, dq. Small amounts of energy keep building in that capacitor until it reaches a steady state, storing the final charge. So I'm incrementing the charges and thereby incrementing the energy levels in the capacitor. So I guess we might have to use some concept of derivatives or basically calculus. So consider some random instant at some instant of time when the charge on this was plus small q and it is minus q at some time instant. At some time instant. What happens? You take out a charge from here and put it over here. So you are basically adding some dq charge on that capacitor. So it becomes plus dq here, it becomes minus dq here. And thereby you increase the energy, thereby increase the energy which is stored in the capacitor by du, by du. At this point, at this moment, there was also a voltage difference between them. There was also a voltage difference between them. And you have taken a dq charge from here and taken it to a higher voltage. What happens when you take a charge from lower voltage to higher voltage? Its potential energy increases. Its potential energy increases. Agree or disagree? A charge going from lower voltage, negative, lower, to higher, positive, what happens? The potential energy increases. Exactly what is happening. So can I also say the work done to move the charge gets stored or goes into increasing the potential energy of the capacitor. Potential energy of the capacitor. What is that work done? dW. What is the increase in the energy? That is du. What is dW? It is, we have seen this in electrostatics, work done on a charge is the charge itself multiplied by the voltage difference. That is basically du. Oh, wait a minute, do I know the value? Do I know the value of voltage? Somehow, yes. The voltage value, oh, by the way, this was dq, so sorry. The voltage is nothing but Q by C, the charge at that moment upon the capacitance. Voltage changes, charge changes. Voltage changes, charge changes. The voltage keeps increasing, charge keeps on building. That's all. Perfect. So now I know what to do next. I know what to do next. U will be equal to integral of du, which is, when I integrate du, that means I'm integrating this whole expression, out of which 1 by c is a constant. So it will be just integrating q dq from original to the final. Here also understand, initially there was nothing present to the final. This 0 corresponds to this state. No energy, no charge. No charge, no charge, no energy. This state is exactly the original initial state when nothing was there on it. What is q dq's integration? Q dq's integration is nothing but capital Q square by 2. So it will be capital Q square by 2 minus 0 square by 2. The whole thing, you will have 1 by c over here, 1 by c over here, which is Q square divided by 2c. So the energy stored in the capacitor is charge square by 2c. You can write it in other forms also. Q square by 2c, half into qv or half cv square. How do you write that? Well, simple things, guys. Let me show it to you. Very straightforward. Because energy stored was half q square by c. Using the formula, q is equal to cv. So it will become cv whole square. Half is there divided by c. So half c square v square by c. cc cancels. So it will become half cv square. So energy is half cv square. This is one way. You can also do one more thing over here. Energy is half cv square, right? So I can just write half cv into v. What is cv? cv is basically charge, so half qv. So energy is half q into v. So all these forms are equivalent. Half cv square, half q square by c, or half qv. One and the same thing. Is that okay? Understood how it comes? Very good. Usha, it is available, bacha. Jungle Book. What are you saying? Just check it out. See, physics, electrostatics, field and potential part 2. This is Gauss law. This is a YouTube class. Gauss law, correct? We have got smiling teeth. Yes, Gauss law and applications, it is there. Perfect. Okay, go ahead. See lecture notes and DPP. Everything is there. Okay, it is uploaded. It is electrostatics part 2 only. Just that we are doing Gauss law over there. Now there is one more thing over here, and that is, observe carefully now. Imagine, imagine an electric field, non-uniform or uniform, doesn't matter. Something like this, some electric field somewhere. You consider a small region. You consider a small region, maybe somewhere here, the small region. And in that small region, if you show it in a little bit enlarged manner, zoomed in manner, you will see in that region, because it's a very small dV volume, you will see that the electric field is roughly constant. Isn't it looking like a small capacitor? Small, teeny, meeny, chintu, mintu capacitor? Isn't it looking like a small capacitor? Oh, yes, sir. It is definitely looking like a small chintu mintu capacitor. Perfect. So what are you going to do, sir, over here? Fine. What is the energy stored in that chintu mintu capacitor? Well, that energy stored in that chintu mintu capacitor is half C V square. Can I write that capacitance as, it's an imaginary capacitor, it's okay, if it will have some area and some distance between them, okay, I can just write it as epsilon naught A divided by D. And voltage, well, I know electric field is nothing but dV by dr. So uh, voltage will be nothing but electric field into that distance and then the whole square. Electric field into that distance, the whole square. Correct? Voltage is E into D, because E is V by D. So V is E into D. As simple as that. So let's see what happens next. This will become half epsilon naught A E square into D. One of the D got cancelled. I take these A and D separately outside and bring it below U. So U divided by A into D is equal to half epsilon naught A square. You might be wondering, why did I do that? What is A into D, guys? What is A into D? Well, let me show you what exactly I've done. This is like taking a small cube over here. This is like taking a small cube over here, separated by small amount, dx. Area of the sides is A. A into D, area into distance, is the volume of that small element which I have chosen. So it is nothing but the volume of that small element. So U divided by volume is half epsilon naught E square. This energy per unit volume is called as the energy density. So that symbol is rho U, density, but for energy is half permittivity into the field at that point square, into the field at that point square. That is the formula, guys. This is energy density. This is called as electric energy density, electrical energy density. Having the unit, joules of energy per volume, so joules per meter cube, joules per meter cube. Got it? Yes. So this is how you derive it, the energy density formula. You have derived it not for just, uniform field, but any non-uniform field can be thought of small chunks of parallel plate capacitors. In each such parallel plate capacitor, the field over there is approximately uniform, and then using the energy formula, you can derive the energy density. What a beautiful derivation, guys, and what a beautiful formula. Let's start with some questions. Find the energy stored in a capacitor of a capacitance this much when charged to a voltage of this much. Come on. How do you find this out? How do you find this out? Find the energy. What is given? Capacitance is given, voltage is given. Which formula do I use? Out of all the three formulas which I have, half CV square, Q square by 2C or QV. Well, capacitance and voltage. So half CV square. Capacitance 100 micro means 10 to the power minus 6. Voltage 20. So 20 square. 2 square is 4 by 2 into 10 to the power 2. From here, this is 10 to the power minus 6 and this 2 zeros, so which is again 10 to the power 2. So that is 2 into 10 to the power 4 minus 6, so 10 to the power minus 2 joules. So 2 into 10 to the power minus 2 joules, which is 0.02 joules. Perfect. This is the same as writing 0.02 joules. Very, very small energy. This is practical. So you should have an idea of how much energy is stored. You cannot expect, sir, will I be able to store some 57 horsepower into time, whatever, kilowatt hour amount of energy? No, 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 not so much. Very, very little. It's a small amount of energy which you can store in the capacitors. But that itself is going to do our job, whatever application we have. The charge on a capacitor is increased by 2 coulomb. Then the energy stored in it increases by 21%. The original charge on the capacitor is how much? That's the question. Okay, let's think about it. So here the charge is increased, energy stored increases by 21%. Okay, let's say our old energy was U. The new energy will be U plus 21% of U, because the energy stored increases by 21%. What is 21%? It is nothing but 0.21 fraction wise of U. So it is 1.21 times of the old energy. That is our new energy stored. Okay. What is the old energy formula? Old energy formula is half capacitor's charge. Okay. Find the original charge. Half, I will use Q square by C. This is a good formula. And over here, this will be half new charge square divided by C. Now wait a minute. U is half Q square by C. So why not use this U? Why not use this U as this one, which is nothing but half into small q square divided by c is equal to half capital Q square divided by c. 2c cancels. 2c gone. So I will get q square is equal to 1.21 times small q square. Taking roots, it will become 121 is a perfect square, so it is square of 11. So 1.1 square is 1.21. But it is clearly given to me. The charge on the capacitor is increased by 2 coulombs. The charge on the capacitor is basically increased by 2 coulombs. That means capital Q is the old Q plus 2. This is 1.1 times of Q. Is that clear? Everybody? Till this point? Everybody, till this point, is it clear? Yes. So, what will happen? Take that Q on the other side. It will become 0.1 Q. So therefore, small q will be nothing but 20 coulombs. So where is 20 coulombs? It is there over here. Option B for IIT Bombay. That's how you solve it. Hello, King Jesus. Welcome, everyone. Join in. Very nice. Awesomeness. Moving on to the next question coming up on your screen. This is there in Tattva module. This Tattva module, it is there in this. So we are solving this question from Tattva. Keeping the voltage, the charge source is constant, what would be the percentage change in the energy stored in parallel plate capacitor? Separation between the plates were to be decreased by 10%. Keeping the voltage constant, very important. Voltage is constant. That means charge will change if capacitance changes, okay? Because Q is equal to C into V. This being constant, charge is directly proportional to the voltage. Sorry, voltage being constant, my bad. Voltage being constant, charge is directly proportional to the capacitance, but capacitance is epsilon naught A by D. This and this are constant, so the charge is inversely proportional to D. Wow, the charge is inversely proportional to D. Here it is clearly mentioned the distance between the plates is changed. Okay. Now, if the old distance was d, what would the new distance be? Because the distance is decreased by 10%. So d minus 10% of d. What is 10% of d? It is 0.1. 0.1. 10% of d is basically 0.1 d. So it is basically 0.9 d. That is the new distance. That is the new distance. Perfect. So if I have to take the ratio q new, which is here, divided by q old, it will be distance which is old by distance which is new. The new charge I do not know. The old charge is q. The old distance was d. The new distance is 0.9 times of d. d cancels. So therefore, the new charge is basically how much? Q divided by 0.9, which you can also write it as 10q by 9. 10q by 9. Yes. What would be the percentage change in the energy stored, they have asked. So if the charge has changed this much, guys, uh, uh, we can find, oh, we had to find the energy change, not the charge change. I'm so sorry, guys. I'm so sorry. This was not needed to be done because we could have directly done it using energy formula. But anyways, I did one type of question if charge was asked. Let me do it for energy change now. Okay. Energy formula. What is the energy formula? Energy formula is half CV square. Okay. And capacitance is epsilon naught A by D into V square. VAE2, everything is constant. So energy is indirectly proportional to D. Oh, that means I'm going to get the same answer. So U new divided by U old will be d old divided by d new. This is just like that charge formula. So solving it similarly, I'm just going to get it is old uh, into 9 below and 10 on the top. So it will similarly be nothing but 10 times u divided by 9, just like before. Okay, just like before. So if you have to find the percentage change in energy, it will be nothing but the difference, which is 10u by 9 minus old divided by old multiplied by 100. U will get cancelled. 10 by 9 minus 1, which is nothing but 1 by 9 multiplied by 100. So basically it will be 100 by 9%, which is going to approximately come out as 11.1, which is perfectly fine. Yes, 100 by 9 will be 11.1. Perfect. Yes. So coincidentally, even if the question was for charge, the answer would be same, because the inverse relationship was the same mathematically for whether it was charge or whether it was energy in this situation. Okay, otherwise it would have been completely different. Okay, perfect. Let's move on to the next question on your screen. Okay, so we have come to dielectrics now. After that, we'll solve more questions, I guess. Okay, ready for it, guys? What is dielectric and what effect does it have and all those things? Ready for it? Okay, let's do. Now, see, I have told you before this also that when electric field goes through vacuum, right, it has a different strength, but the moment it enters some medium like water, ceramic, wood, glass, etc., just like light changes the speed, so same way, understand, even the magnetic and the electric fields, they change their strength completely. And that comes because of the polarization. If you want to know more about it, I would suggest watch this particular lecture of electric field and potential. Just check this out. Okay, I've discussed in detail how it changes. Okay, what happens over here. This was done recently. Electric field due to dipole, all these things we have discussed. Okay, see this electric field in an external medium, all these things. So just check that out. Okay, so the concept of dipole was discussed over there. Now, this any medium has this ability to reduce, to change the electric field which enters the medium because of this dipole formation. I'll explain this to you, what exactly happens. Okay, I'll explain this to you, what exactly happens. See this. Imagine in vacuum, the electric field was, for example, E naught in vacuum. Okay. Now, imagine there is an atom. Imagine that there is an atom like this. An atom has positive charges, protons, and electrons, which are negative charges. Now, usually what happens is the positive and the negative centers coincide, but there could be some offsets here and there. Maybe the electron cloud has shifted. Maybe it's a molecule. So the electron cloud has been pulled, like in H2O, right? The oxygen becomes more negative than the hydrogens. So the electron cloud might shift. So in a molecule, or even for an atom, if there is some disturbance in the electron cloud, you might see the positives and the negatives might not coincide with each other. So probably you might see maybe the positive is here and maybe the negative is here. This becomes a polar molecule or a polar particle. So right now this is polar in nature. This is polar in nature. So it has a dipole moment for sure. And the dipole moment, remember, it always goes from negative to the positive. So there is a dipole moment. There is a dipole moment. There is a dipole moment. I hope this is absolutely very clear. Now, if this external field, when this external field, when this external field is passed through such a polar molecule, what happens? It experiences a torque. It experiences a torque. So there is a torque on it, which is just given by P cross E, which is just given by P cross E. So it rotates. And once it rotates, it comes to equilibrium state. It comes to stable equilibrium eventually. It comes to stable equilibrium eventually. So you will have the positiveness over here. You will have the negativeness over here. You will have the external electric field traveling like this. And in such a case, the torque will be 0. Now imagine in a solid, in a liquid or any object, how many such molecules will be there? How many such teeny mini dipoles will be there? How many such molecules will rotate and align themselves? That is incredible to imagine. So if you probably just think about a solid or a liquid, just one second. If you think about a solid or something like this, you will notice that once external electric field is passed, once that external electric field is passed, you will have so many such teeny mini dipoles with positives on the one side and the negative on the other side. Many of them. I'm not showing many, I'm just showing very few. So many dipoles oriented like this. So once these dipoles orient themselves like this with their dipole moments, in this particular direction, in the direction of the external field, dipoles arranged parallelly to external field. What happens next? This was your external field. What happens next? These dipoles themselves have their own electric field. Do not forget that. These dipoles themselves have their own teeny mini electric field. So how does that electric field look like? Well, it looks something like this. If this is our electrical dipole, the electric field lines always start from the positive and go towards the negative, right? So they will basically, one second, I'll just mention it here. This was your positive, this was your negative. The electric fields go something like this, go something like this, like this, like this. You can see it's going opposite. It's going opposite to the dipole moment, roughly backwards. Now just imagine there were many or some 3 or 4 such dipoles. 3 or 4 such dipoles. How would the field lines look like? It would look like this, like this, like this, like this. Then the next field line, it could not enter here because of the gap in between, which is not enough. So you will probably see the next electric field line, it tries to enter, but it can't, tries to enter, can't, tries to enter, can't, tries to enter, yes. Next, it can't cross. Remember, electric field lines can't cross. So to go like this and come like this. Same thing below also. Same things will happen below also. So the next electric field line does not have enough space to enter. So it will come from here. Next electric field line will go like this and enter from here. Now imagine many such dipoles are there, infinitely many, all small dipoles and placed very close. What you will see is that all these dipoles, all these teeny mini dipoles, which are there everywhere, which are there everywhere, which are there everywhere, they will create a reverse electric field which is induced in the opposite direction, which is induced in the opposite direction. So this is now our induced electric field, which is opposing the external electric field. Hence, the net electric field, inside that medium, magnitude wise, will be that external electric field minus, because it's opposite, minus the induced electric field. Hence, you can see that the net electric field is always less than the original external electric field, is less than the original external field due to the induced field. Is that absolutely clear? Everyone with me on this? Very good. Awesome. So it reduces usually k times. That is what we refer that constant as. So that E net is actually E naught divided by k. This k is called as the dielectric constant of the medium. This is called as the dielectric constant of that particular medium. This is called as the dielectric constant of that medium. For air, it is 1. For wood, paper, etc., it might be 10, 20, 100. For ceramics, it might go up to 300 or 400. So more dielectric strength means lesser electric field will be present inside. Now, this is the whole concept, okay, of the medium which is present between the plates of a capacitor. Now, this experiment was, by the way, performed by Michael Faraday. Faraday installed multiple materials and he saw that the capacitance changed once you place some medium inside between the plates of the capacitor. So, if a capacitor is charged, the charges on the plates produce the external field, which then end up polarizing the medium inside, which then change the electric field. Now, here is my argument. Here is my argument. Observe this carefully. I have explained you what is dielectric constant, etc. Observe this carefully. Imagine there is a capacitor and it is connected to a battery. So there is some electric field here. There is some electric field here. There is some charge on this, plus Q, minus Q. Now what I do is, what I do is, in between these plates, I add some material. What do? I add some material in between them. Let's say like this. I have added some material in between. I hope you can see this small color. I have added some material in between. Now, the moment I add some material in between, what do you think will happen? That will try to reduce the electric field. Think about it. This material which I have placed in between over here, this material which I have placed in between will try to reduce, electric field. How many times? 1 by k times. K is a number more than 1. So if I make it half times 1 by 3 times, that means it will reduce that many times. But my argument is, my battery is the same. The distance between the plates is the same. How can electric field change? But electric field is voltage divided by distance. Neither the battery change nor the distance change. So it must be a constant. It must be a constant. These are conflicting results or arguments. Medium present inside says that the field should reduce. But if I go by this logic, voltage by distance, it should remain constant. So what exactly is happening? This has to be true. This is also true. But what if I tell you that both can be true by thinking little bit differently? Think like this. See, the electric field is same as before, 100%. It's just that the electric field reduced to become this field. Actually, think if this slab was not there, maybe it would have been many more times, but it reduced 1 by k times to become this new electric field, which is still the same as before. So ideally, electric field should have increased to reduce it k number of times so that it still remains as V by D. And this external field can increase in only one particular way. It can increase in only one particular way by increasing the charge. So imagine now there is more charge, there is more charge over here. So it produces more electric field between the plates, but the medium ends up reducing it to keep the net electric field constant. So this E is not the external, it is the net electric field. It is the net electric field, and this capital E over here is that external electric field between the plates. Is that external electric field between the plates, which has now reduced to k times. What an interesting concept. So to maintain the same field and at the same time to reduce that external field k times, the charge stored on it increases. So the charge increase creates more external field between the plates, But because the medium is present, the effect is not felt at all. It's like saying, observe it. My old field was 100. I had 100 laddus. Okay, old field was 100. I increase it. To 200 laddus. I increase it to 200 laddus. Okay, these are the new laddus. But I will allow only half of the laddus to be eaten by you. So finally, you will end up eating 100 laddus only. So this 100 is the old electric field. The new electric field is because of extra charge, but this number 2 is because of the dielectric, and you end up getting the same electric field as before. That is what it is. Did you understand this concept? Yes or no? Did you understand this concept? Yes or no? Think about it. Okay. If this is understood, then we can proceed ahead. So the charge stored in it has increased. So the charge increases. Hence, I can say that the capacitance increases. So putting a medium in between increases the capacitance that many number of times. So whatever formulas we had, effect of dielectric on capacitance, I think I can just say the dielectric medium, increases the capacitance k number of times. So if the new capacitance is C new, it will be C old multiplied by K. That's all it does. So all our existing formulas will look something like this. C for a parallel plate capacitor will be epsilon naught A divided by D. Then C for a cylindrical capacitor was 2 pi epsilon naught length divided by log of B by A. And C for a spherical type was 4 pi epsilon naught 1 by A minus 1 by B. So if you fill it with a medium, you just have to put K over here, K over here, and K over here. That's it. That's the only change. So the old multiplied by K times. That's the only difference. Okay. As simple as that. All right. So let's do some variations in this where you will be connecting it to a battery and then you will be not connecting it to a battery, and then what is the effect on the capacitance, charge, voltage, energy, etc. So let's think about it. Say for example, now you have connected it to a battery. The moment you connect it to a battery and then you insert a dielectric medium, obviously the voltage first of all should remain constant. Voltage is obviously remaining constant. Whereas if you do it without the battery and you put that slab in between, then it is the charge which remains as a constant. Then the charge will remain as a constant. This is the primary argument. Now let's talk about capacitance. We know when you put the slab, then the capacitance increases k times. Now whether the battery is there or not there does not matter. Here also capacitance increases k number of times. Now in this case, if you talk about charge, since Q is equal to CV, voltage didn't change, capacitance increased. That means Q also will increase k number of times. Whereas when battery is disconnected, since Q being equal to C into V, Q did not change, capacitance increase, voltage should reduce. Therefore, voltage decreases k times. Do you guys understand it? Till this point, is it clear? Give me a thumbs up. And if you have forgotten to smash the like button in the session, do that right now. Many of you forget. Every time you need to be reminded. Do that right now, guys. Yep. All right. You're scoring 98. 98 is less, no? 98 in, what have you written? 98 in my mock test. 98 is less. You have to target bare minimum 200. Now, next concept, energy. I will use the formula half CV square because voltage was a constant. Capacitance increased k times. So, therefore, energy increases k number of times. In this case, when the battery is disconnected, charge being constant, I will use the formula U is half Q square by C. Q is constant, capacitance is in the denominator. The denominator increased k times, so the ratio will reduce. Therefore, the energy will decrease k number of times. energy will decrease k number of times. Perfect. What about the electric field? Let's think about the electric field. Voltage is a constant. So electric field is voltage divided by distance. Neither voltage change nor the distance change. Therefore, electric field remains constant. It did not change when battery was connected. Whereas when you go to disconnected, battery being disconnected, and if you use electric field is V by D, D did not change, but the voltage decreased. Therefore, the electric field also will decrease K number of times. Voltage will decrease, so energy will also proportionately decrease K number of times. I hope this is very, very clear. Absolutely. Awesome. Great. So let's do some questions now. Ready for the last segment of this chapter? Remember, there is lecture 2 of current electricity also and capacitors also. Both of them will be together. I hope that was very, very clear when I explained it to you. Some people are still confused, so I'll just explain it again. Current electricity lecture 1 done. Today capacitors lecture 1 done. After this, both these things combined, you will have lecture 2 of capacitors and current. Lecture 2 of capacitors and current, where we'll be doing parallel, series, combination, all this combination of capacitors and circuit, combo problems and circuit problems, Kirchhoff's law, current law, all those things. We'll be doing it in lecture number 2. Okay, I hope this is absolutely clear. Okay, chalo, let's do this question. There is a charge capacitor, and what are we doing with it? Energy is this much. What will be the energy stored when air is replaced by dielectric of constant K, Q remaining the same? Q is the same. So, if Q is given to be a constant, capacitance will increase. How many times when air is replaced by dielectric constant? K times. K times it will increase. This is what will happen to the capacitance. So, what will happen to the energy? Charge the dielectric constant. What will be the energy stored? Energy is half Q square divided by C. Since the numerator is a constant, easily it can be seen U is inversely proportional to C. So if C increases, K times, naturally U will increase by 1 by K times. Rather, it is good to say energy decreases K times. Energy decreases K times, 1 by K. That is the answer. It decreases K times or it increases by a factor of 1 by K. One and the same thing. Okay, till this point clear? Shall we go ahead to the next question, guys, coming up on your screen? All right, what does it say? This is there in H.C. Verma. So read the question, guys. This is there in H.C. Verma. A parallel plate capacitor is connected to a power supply. A dielectric slab is now inserted into the gap. Find the extra charge which flows. Find the change in the energy. Okay. Is connected to a power supply. That means battery was connected. So earlier, this is how it was. Positive, negative. Now, there is a slab in between. There is some kind of a slab in between over here. So obviously the charge which will be there will also be different. The charge which is there will also be different, right? So there will be different amount of charge over here. Okay, so let's do this question. If you consider the old scenario, if you consider the first scenario, old, when nothing was there, then charge will be CV, capacitance 100 micro, so I'll just put 100 micro, voltage 200, voltage is 200, so it will become 20000 micro coulomb, which is, again, if you take these three zeros, it will just become 20 millicoulomb of charge. That is your old charge. Now find the extra charge, find the change in the electrostatic energy. What is the original energy? And original energy will be half CV square, capacitance being 100 micro, voltage being 200 square. 2 square is 4, 4 by 2 is 2 into 100, which is 10 to the power 2 into micro into 10 raised to 2 raised to 2 is 10 raised to 4. So this will become 10 raised to 6 and this is 10 raised to minus 6 because it is micro. So it will just become 2 joules. Perfect. So this is the original initial energy. This is initial. This is also initial. Now let's look at the final. Because what have you done? A dielectric slab constant 5 is inserted. So capacitance, second time, new one. New capacitance will be 5 into 100 microfarad. So what will be the final charge? It will be nothing but 5 times, or rather, because it will be new capacitance into voltage. Voltage was the same, capacitance increased 5 times. So charge will also increase 5 times. So it will be 5 times of the old charge, which will be nothing but 5, it will be nothing but 5 times of, yes, it is 20, which is 100 millicoulomb. So how much charge has gone? It will be final minus initial, which is 100 minus 20, which is 80 millicoulomb. That is the first answer. How much extra charge went through that supply? What is the change in the energy? What is the change in the energy? Let's do that also. What is the change in the energy? What is the change in the energy? Final energy, because it is half CV square, capacitance increased 5 times. It will be 5 times of that old energy. So 5 times of 2, 5 times of 2, which is basically 10 joules. So how much is the change in the energy? Final minus initial, which is basically 8 joules, which is basically 8 joules. Is that absolutely clear, my dear warriors? Yes? Awesome. So we solved both the answers, 80 millicoulomb and 8 joules. Perfect. We did it. Awesome. Now, this much is done. Let's go to the next question. Let's do the next question coming up on your screen. Parallel plate capacitor of capacitance is charged by a battery connected between its place to a potential difference of 12 volts. The battery is now disconnected and a slab is inserted. A change in the potential energy after inserting the slab. Guys, don't you see? It is very much similar to the previous question, just that now the battery is disconnected. That's the major difference. Question is the change in the potential energy. First of all, the initial potential energy using the formula half CV square will be half, capacitance is 12.5 pico multiplied by voltage, which is basically 12, right? So 12 square is 144 and 144 into 12.5 divided by 2 will be the original energy. Is that right? Is that right? Okay. But we can also probably simplify it later on, maybe not now. We'll just keep it as it is. Maybe some factors might get cancelled. Who knows? Now, when you disconnect it, when the battery is disconnected, what remains same? The charge. The charge remains the same. The charge remains the same. So using U final, using half Q square by C concept, energy is half Q square by C. Q is the same. So the energy indirectly, energy is inversely proportional to the capacitance. Because you add a slab, because you are adding a slab, it will increase K times the capacitance. That means the energy will decrease K times. The energy will decrease K times. Hence, our final energy will be our old energy divided by the dielectric constant, which means whatever is that old, you divide it by the number 6. You divide it by the number 6. That's it. Now we can find what is the change in its energy. So the change in its energy will be this minus this. If you do ui minus ui by 6, so it will be 5 by 6 times of original So it will be 5 by 6 multiplied by that whole number which was there. This ui, this ui, this ui, which I calculated over here. 1 by 2 into 12.5 pico into basically 12 square. That's it. So do the math and you will get the final answer for delta U. This answer comes out to be as, I think, 750 into 10 to the power minus 12, which you can write it as 0.75, 0.75 picojoules, which is 750 into 10 to the power minus 12 joules. Pico is 10 to the power minus 9. So you shift the decimal, you get 3 extra negative powers of 10. And 10 to the power minus 9 and 10 to the power minus 3 will become 10 to the power minus 12. So that's what will happen. Okay, that's it. That's the answer for this. That was the last question which we did today. Okay, awesome. Now, make sure that you are practicing a lot of questions. Make sure you are doing the DPPs which have been given to you. Make sure that you are very regular in attending all the classes out here, okay? Because if you miss any of the classes, it's going to be a big headache for you only. So kindly make sure that you do not miss any of the classes. You are very regular in the ROAR series. You mark your attendance by liking the video. Also ensure that you are solving the DPPs which is there in the Jungle Book. The link is there over here in the description box of any video, right? You can see Jungle Book. All the sheets are updated on a regular basis. If anything is not updated, don't worry. Within 2-3 days also, it will get updated. Okay. Next lecture, lecture 2 of current, electricity and capacitors combined together, we'll be solving circuit problems. Circuit problems. Yeah. It will be continuation. Yeah. Does Vedantu offer course for class 12th right now? Yes. There are multiple courses. So you can see you have either online or you have offline. Now, as you can see, I think probably in the banner below, you might be seeing offline courses. The last batch for 12th standard is happening right now. So you can click on this particular link, fill out these details. You can see these are the centers. Like you can see right from Pune, Muzaffarpur, Bhubaneswar, Srinagar, Jammu, Hyderabad, Vishakhapatnam, Vijayawada, Chennai, Coimbatore, Trichy, and Bangalore. All these centers, last batch is starting right now for 12th, 11th, and droppers. So you check out that. Second thing, if you're like, no, sir, I don't want offline, I want to study online only, I'm comfortable with that, or whatever your personal choice. So then you can fill out this form with your details. You can say, I'm in class 12th, I am preparing for JEE, I want it online, and I want a call back. Click on yes, don't say no. And then fill out any doubts that you have. Pure English batches are starting. I would say you can join a 12th batch or you can even join a dropper batch. It's fine. The advantage of 12th batch for a 12th student is the timetables are adjusted for for school going students, plus they also accommodate for board exams. The dropper timetable is such the classes are in the afternoon, and we will not get break for board examinations and all of that. So otherwise, the same level, same content, you will have good questions to practice from. All the same kind of teachers are there. It's just that the batch timings and the timetables will be slightly different for class 12th and the dropper students. And yeah, for dropper students, you will have class 11th and 12th standard syllabus being taught completely, or class 12 students, first priority will be given to 12th, and then you will have 11th standard syllabus which will be started. Okay, so that is what it is. Okay, so just fill up this form details over here and we will give you a call back. Our counseling team, academic team will give you a call back. Is that okay? Fine. Sachidan, sorry. Okay, bye bye Adiksha, bye bye Sadia, bye bye Special Back, bye bye, take care Harish, bye bye everyone, Dharnishwaran. Thank you so much, and I want to see you in the comments. Okay, ready for lecture 2 in the comments, ready for lecture 2. Okay, thank you, bye bye, take care.